Good morning, everyone. This is episode 1 of AlgorithmsThread. I'm your host, David Hermeyer. Not Matt Fontaine, but the next best thing, right? So today I'm going to be talking about division under mod, and also kind of some other operations under mod. In particular, why they work, so you can get a feel for them, and a little bit of intuition on how modular operations work and why they're a thing. So in a lot of programming problems, you'll see like print the answer modulo 10 to the 9th plus 7. And in all of these problems, it's a little daunting if you're new to this and you haven't seen this kind of thing before. So basically, what does that mean? Well, if you imagine you have a circle, and the circumference of the circle is whatever your mod is. Like that's how long it is, how many steps there are to go around the circle. And if you take a certain number of steps, then you'll go around the circle a bunch of times, or you'll go around the circle maybe not even once, but then after you take enough steps, you'll go around the circle, and then you'll keep going around the circle again and again. So if you take like some very, very large number of steps, and then you can tell me where in the circle you would be, that would be equivalent to your value under mod. Mathematically, formally, basically what this means is if you have like some integer x, and then you divide it by your mod, then you're going to get maybe like you get like 7 remainder 3. So then what the value is, if you take something under this mod, the value you're looking for is the remainder, and that's all you care about. So why does this matter at all? Well, the main reason is because in a lot of problems, you have to calculate some number. Like usually it's roughly like the number of ways to do something. And this can be a very, very big number as n, or the size of the problem, gets bigger. So this might have like, maybe it's got like 10 to the 8th digits or something. So it's like a very, very large number. You might not even be able to print what that number is, even if you could calculate it. And as the size of the problem increases, this number might increase even more than linearly. Like even the length of the number might get huge really fast. So it's difficult to test the runtime of certain solutions if the numbers you're dealing with get to be this big. The problem devolves into not like how do you solve the problem in an efficient way, but how do you add two numbers, or how do you multiply two numbers in an efficient way. And that's not really fun for competitive programming, and it's also not really an interesting problem to solve, kind of, because then it's just a lot of nonsense that you have to do the same thing every time with. So instead of doing that, what you do is if you calculate the mod of this value under some big prime, and a lot of times you choose 10 to the 9th plus 7 as your prime because this is a prime number and it's quite big. So if you can calculate the value under this mod, then we can be confident that if we asked you to calculate the real value and gave you enough time to actually do it, and do the calculations with the big numbers, you would be able to figure out what that value would be for real. Because if you can calculate it under the mod of this prime, the chance that you just got this value by being lucky is very small. It's 1 in a billion. So what does that mean? Well, you're counting like the number of ways to go around the circle. So there are, I guess, several different operations you can do. You can do plus, you can do multiplication, or you can do addition, subtraction, you can do multiplication, and then you can kind of do division. But division's a bit tricky, and we'll talk about that later. So addition is pretty clear. If you want to add two numbers, a plus b, and then you want to see what they equal under mod, so we'll call it like under mod of m, then that's a pretty straightforward thing to do. So how do you go about doing it? Well, let's use some real numbers as an example. So for a mod, I'm going to pick 5 because it's easy to keep in your head. And maybe we have some number a, and a is like 12, and b is maybe 19. We want to calculate 12 plus 19, and then we want to calculate the remainder after we divide that by 5. So the actual answer to this problem is going to be 31, and then mod 5 would be 6 remainder 1. So the actual value we're looking for is equal to 1. That's kind of the goal of this problem, to find 1. But one thing we can do to make this problem a little bit easier is we can store this 12 as this is like 5 plus 2, and this 19 is 5 plus 5 plus 5 plus 2, or plus 4 rather. And when we do this, this 5 corresponds to like going around the circle an entire time. So these 5s don't matter at all. We can just ignore them entirely. And all that's left is this 4 and this 2. So 2 plus 4, mod 5. Well, we have this is equal to like 5 plus 1. So this 5 we can ignore, and then we're left with this 1. So basically, if we want to add two numbers under mod, if we want to add a plus b, under like some mod of m, this is going to be equal to a under the mod, because we can ignore all of these 5s over here, plus b under the mod. And then we can take this whole thing, and then we have to mod it again. Because as you saw in this example, you might get the 6, and you might introduce another 5 that you have to get rid of. So this is how we can add two numbers under mod. And the nice thing is, if we need to store some total, we can take the mod at independent steps. So we don't have to calculate the entire total at once, or calculate this entire value of a, like the absolute value, without using the mod. Same thing with the b. We can just calculate the entire thing using mods at each step. And that makes us be able to solve the problem without needing to use very large numbers. So subtraction is pretty much the same as addition. You're just undoing it. And subtraction is the same thing, so I'm not really going to cover that. It should be pretty clear that you can take the mod at each step. But when we get to multiplication, it might not be that obvious that you can take the mod at each step. It turns out that you can, and I'll kind of explain why. So if you have a times b mod m, what I'm going to say this is equal to is it's equal to a mod m times b mod m, and then this whole thing we have to mod again. So why is this the case? Well, let's do 12 times 19 again, under mod of 5. So what this is equal to is we're going to have a bunch of 12s that we're adding up. And the number of 12s we have is we're going to have 19 of them total. And we want to figure out what this is equal to. Well, we can represent these 12s as like 5 plus 5 plus 2. So let's do that really quick. And it should be pretty clear that if we do this, all of these 5s aren't really relevant, because a 5 is just going around the circle by itself. So this is the same thing as just adding a bunch of 2s. So that tells us that there will be 19 of them total. So in other words, 12 times 19 is the same as 2 times 19 if we're working mod 5. And you could use the same argument to turn the 19 into a 4. But there's another way of thinking about it that I think also is kind of helpful, which is if we're doing this 19 times, then that means that's the same as, like, conceptually, we can do it 15 times. And then after we do it 15 times, we can do it another 4 times. Let's make this a bit neater. So now the thing to notice is that 15 is divisible by 5. So we're taking some whole integer and multiplying it by something that's divisible by 5. And when we do that, we'll definitely get something else that's divisible by 5, because they share the factor from 15. So this part will just go away for that reason. And that's why for multiplication, we can take the mod at each step, like we do here. And we're totally safe to do that with multiplication. So that handles most of what we need for most problems, and for a lot of problems you can just use addition, subtraction, and multiplication to count the number of ways of doing something, often with like dynamic programming involved as well. And it's also pretty clear why those work. So the confusing part is, what if we want to take two numbers and we want to divide them under mod? So what if we have like some integer a, and then we have some integer b, and then we want to calculate what a divided by b is under mod of m. This is a bit tricky because it isn't really obvious how to do this. And the other thing is, when we're calculating numbers under mod, it doesn't make sense to have fractional numbers. So the number like 3.25, for instance, doesn't really make sense. Now you can make it kind of make sense, and I'll talk about that at the end of the video, how to kind of represent this. But it isn't, like, this decimal part isn't usually super helpful to think about under mod. So instead, what we're going to do is we're going to assume for the moment that this is some integer. So let's use the mod of 5 again, because I think that's kind of helpful. And maybe we want to calculate 12 divided by 3. So we know this is an integer, 12 divided by 3, because we know it's 4. And it would be really nice for us to just like be able to say, yeah, this is 4. The issue is, this 12, if we're storing it, this might be some very big value, and we might have this like very large intermediate value, So we're going to have to take it under mod partway through the problem. So really what we're looking at is we're looking at 2 divided by 3 under mod of 5. And it isn't really clear what this is going to be because this doesn't look like it would evaluate to 4. So instead, we can't really do division in this sense because 2 divided by 3, well, it might represent 12 divided by 3. It also might represent 7 divided by 3. Or it might represent, might be 12 over 3. Or it might be something else entirely because we don't know how many times we've taken the mod from this. We also don't know how many times we've taken the mod from the denominator. So it might be 12 over 3, but it also might be 12 over 7 or 12 over 8. And this would be what, like 2/3? So since we don't know that, it's kind of difficult to figure out what we should make this evaluate to, or to do math that would give us that answer. So instead, what we can do is we can use this thing called the modulo inverse. And if we want to find the mod inverse of x, we can write that as x to the negative 1. That's what people usually do. So what we want to do is ultimately we want to calculate what 12 divided by 3 is. And we want to calculate this with respect to the mod of 5. So the great part about mod inverses is they let us do this, effectively do division. So we can multiply by something, but instead of multiplying by it, we're multiplying by the modulo inverse, and that's similar to dividing by that number. So this is equivalent to 12 times 3 inverse, whatever this thing is under mod of 5. So how do we calculate 3 inverse? Well, it's a bit tricky. Basically, what it results in being is we take this 3, and then we take it to the power of the mod minus 2. Why the mod minus 2? Well, I'll explain that in just a minute. But if you take 3 to the mod minus 2, that's equal to 3 to the 3 in this case. If the mod was 10 to the 9th plus 7, it would be 3 to the 10 to the 9th plus 5. That's the power that we would take 3 to, and calculate that under mod. So we want to calculate 3 to this power, 3 to the 3rd, for instance here. What is that? That's equal to 27. And then 27 mod 5 is equal to 2. So 3 to the 3rd power is equal to 2 under mod of 5. So what that tells us is that if we take this 12 and we multiply it by 2, we're going to get some number that's equal to 12 divided by 3. And in both cases, we get 4. This right here is 24. And we can subtract away the 20, and then we'll be left with 4. So that's kind of what the mod inverse looks like. That's roughly how to do it. So now the big question is, why is this possible? Well, here's what it winds up looking like. We can, we're taking some number, let's take the number 2, and we want to find the mod inverse of 2. So it turns out that if we take 2, and we take 2 to the power of 5 mod 5, then we're going to wind up with, that's always going to be 2. So this is true if this number is 5, it's true if this number is 7, it's true if this number is really any prime. So 2 to some prime p modulo that same prime is going to give us 2. And this is true for 2, this is true for any number x even. And this is, I think, Fermat's Little theorem, I want to say. But the mathematics behind this isn't too important, but there's a really nice way of coming up with a concrete example that makes it very easy to remember. So let's look at 2, for instance. So 2 to the 5th power mod 5. What would this, what's a real way of representing this? So let's imagine we have a bunch of strings. Each is a string of A's and B's. So maybe this is some string here. Maybe we have some other string that's 5 A's in a row. Maybe we have some string that's A, B, or BB, A, B, A, for instance. So these are 3 different strings. But imagine we had every possible string that consists only of A's and B's. So the first character can be an A or a B, second character can be an A or a B, third character can be an A or a B. How many strings do we have total? Well, every character has 2 different choices, and there are 5 positions, so we have 2 to the 5th strings total, and there are 32 different possible strings. They're equal to, if you make A a 0 and B a 1, they'd be, if you write all of the numbers 0 to 31 in binary with 5 digits, with leading zeros, It would be all of those 32 numbers. So if we imagine these are all necklaces, we'll call them necklaces, and they're going to be two special necklaces, and the two special necklaces are going to be the necklaces that are all A's, and the other special necklace is the one that's all B's. So we're going to take these two necklaces, and these are very special. So we'll take these and put them off to the side for now. I'm just going to erase them, but you can imagine like taking those necklaces and putting them off to the side. And then here are two examples of, or here are the two necklaces we had left over. So we had AB, ABB, BB, ABA, and we have a bunch of other necklaces. But you can imagine that if we take these necklaces and we like connect them like a real necklace, these are just beads on a necklace, that these are really the same necklace. We can take these these beads here, and we can move them over to the beginning. Right, so this one would go here, this one would go here, and this one would go here. And then after we have that, from left to right, we would have something that looks like this first A, then this B here, then this A, and then this B and this B. And equivalently, that means this necklace is the same as this first necklace. They're really like the same necklace. So now the natural question that follows is, if we have this necklace here, and it's in this order, how many different necklaces are there that look like this? Well, we can start at this A, and that gave us this one here. The other necklace we had started at this B, and that gave us this other one. But really, we can start at any of these necklaces, or any of these positions at all, and we'll get a different necklace. And you can try it, for example, in this string, you'll get 5 different ones. You'll get like AB, ABB, BA, BBA, ABB, AB, etc. And it's very easy to convince yourself that if you have any string here that isn't all A's or all B's, so if it's not all the same, there's some way that you can find that makes it like a distinguishable starting point. There's some lexicographically minimal starting point, and that's a unique starting point. So you can definitely determine that that's like the one identifying like real starting point. That's the letter you could put on the top. And then from that you can find 5 other ways of writing that same necklace if you started at different points. So since we know there are 5 ways of doing this, and this is just for one type of necklace, there are a bunch of other different types of necklaces as well. Maybe this one's like an A and then 4 other B's. And maybe this one's like a B and then 4 A's. And then we have got like some other things here as well, like maybe 2 B's and then 3 A's or something like that. We have all of these different ways of representing, or all these different like identifying necklaces, but the important part is each one has 5 ways of like turning it into this string of 5 letters. And that means that the total number of these possible strings is a bunch of these groups plus the 2 that we removed. And those 2 that we removed are all A's and all B's. So what that means is that in this example, we had 2 different types of characters. These 2 different types of characters were the A and the B, and we had 5 different positions. And it's true that if we had 3 different characters, well then there would be these 3 different strings we'd have to remove. We'd have to remove all the A's, all the B's, and all the C's, like strings of all A's, B's, and C's. And this is for the 5 positions, which is why there are 5 different starting points. If we had 7 different starting points, then there would be 7 ways to do each of these necklaces would be representable in 7 different ways, except for these 3, and each of these 3 would only be represented in 1 different way possible. Now that's true whenever this number, this exponent, is prime. The issue is that it doesn't work when it's not prime. And that's why in all of these problems, all these competitive programming problems at least, the mod that you have to calculate things under is almost always prime. And that means you can use this nice trick to use division. So let's kind of finish it up. So we know 2 to the 5 modulo 5 is equal to 2. What does that mean? Well, what's 2 to the 4 modulo 5? Well, we can see that if we multiply it by 2, then we'll get this 2. So it makes sense that this would be 1. Because if we multiply it by 2 again, then we get this 2. Well, okay, fine. What does 2 to the 3 modulo 5 equal? Well, if we multiply this number by 2, then we're going to get 1. Which means this number is the same as taking some other number and dividing it by 2. So this is like roughly 1/2. So we can take 1/2, we can multiply it by 2 to get 1. We can multiply this by 2, and we'll get 2. So let's check this really quick. So let's take 3, which is really, so I guess let's do 8 divided by 2 under mod of 5. So this should be 4. That's what we're looking for. So this 8 under mod of 5 would be 3. 2 inverse, we've just calculated, is 2 to the 3. So this would be 8 mod 5. So this would be times 3. This is going to be equal to 1. That's an issue. What have I done wrong? So 2 to the 3 mod 5. 2 to the 3 is 8. Under mod 5 is 1. So, oh no, that's fine. So yeah, 3 times 3 is equal to 9 under mod of 5, which is equal to 4. So 8 times the inverse of 2 is the same as 3 times 3, and that turns out being equal to 4 again. So that's how you do division under mod. Now, I was talking about this assumes that this p is prime, and it doesn't work when the power isn't prime. So let's look at a quick example of that just so we can see why this is true. So let's say the power is 4. That's a good small number to think about. So if we have, that corresponds to having just 4 numbers here. And the interesting thing about this is like some string AB, right? Now imagine we have this string. What we can do is if we start at this position and look at this string, that turns out that it's the same string as if we start at this position and go like this. And that's because 4 has a divisor that is smaller than it that isn't 1. So that's like the same thing as it being prime, really. So here we represent this string AB. We've just counted this twice. So that's why this is only true for prime mods. If it's not prime, there are other much more complicated ways of dividing. Sometimes you can't always divide because there isn't always an inverse. And sometimes you need to split the prime up into, or split the composite number up into all of its prime factors in order to divide. So that's why division works. The last thing I'd like to talk about is how to do these p times q inverse problems. So in a lot of Codeforces problems, they'll ask you to calculate the probability of something happening. And you represent this as like some number p times q inverse, where what you're, like the number this represents is going to be p over q. So some rational number. So maybe the chance of something happening is like 10 over 3. And this is equivalent to, I guess, 3.3 repeating, right? The common way of writing it, I guess, is like that. So this is the number we're representing. This is maybe like the expected number of times that you'll roll a multiple of 3 if you roll the dice some number of times, I guess. I don't know. Yeah, so like this is just like the expected number of times something will happen. It can really be anything. But the answer is 3.3 repeating. So what they want to get, or what the answer you should actually give, is going to be 10 times the mod inverse of 3. And this is the number you print. So it turns out that you can just represent this number as a single integer under mod. And every time you want to take this number and you want to multiply it by something, so if you have this p over q and you want to multiply it by some constant, whether this constant is like an inverse or it's some positive number that you want to multiply the numerator by, you can just take this c and you can multiply it by whatever this integer is, and that'll give you this new valid answer. The other really nice thing that you can do is if you have this p and this q and you want to multiply it by some other fraction, a over b, then this is going to be equal to pa over q times b. So what if we stored these as, instead of storing them as like a numerator and denominator separately, we just stored them as multiplicative numbers and mod inverses? Well, then we would have p times q inverse, whatever this number winds up being, this q inverse. And then we want to multiply this by a times b inverse. Well, that'll give us p times q inverse times a times b inverse. I guess I just wrote the same thing twice. But since multiplication is commutative, this is the same thing as p times a times q inverse times b inverse. Where, again, these are just numbers. This q inverse is just like some number. It's q to the power of the mod minus 2, but that winds up just being some integer. Now this right here is the exact same representation as this. And that means if we want to multiply, we can just multiply these two integers and then it'll maintain the right answer. We can also do the same thing with addition and subtraction, of course. So if we have p over q, we want to add a over b. This is going to be equal to p times b plus q times a over q times b. And if we, so I guess this is what we're representing. So this is the same as pb times q inverse b inverse plus QA times Q inverse B inverse. So what I just did is this is like equivalent to PB over QB, which is where this part comes from, plus QA over QB, which is this part here, which is where this comes from. So that's where all that math comes from. But now you'll notice that B times B inverse is equal to 1. So this part is the same as P times Q inverse. And this part here, we can notice that Q times Q inverse is also equal to 1. So this turns into A times B inverse. And this right here is just the exact same thing as what we started with, except if we just ignore all of these numerators and denominators entirely and just store all of our numbers as P times Q inverse. So this lets us work with fractions, but we can treat the fraction as just like some number under mod. And if we want to add or multiply two fractions, we can do this very easily just by adding the two numbers or multiplying the two numbers and taking the result under mod. And we can subtract because it's just the same as addition. And we can divide because it's just the same as multiplication, but we just take the mod inverse of these two. So what does that look like? Well, if we have P over Q plus, I guess division is multiplication, right? So A over B, I guess we want to divide, right? So divided by A over B. This is the same as P over Q times B over A. Now this part right here is just the multiplicative inverse of this. That's all that is. So if we want to do this division, we can just take the mod inverse of this thing here, and that'll give us exactly what we want. So that is all of the fancy stuff you can do under mod and why it turns out to work very nicely. The moral of the story is that you can use necklaces in order to count and like convince yourself that Fermat's little theorem is right. So if we take x to some prime, modulo that prime, then we'll get x. And that's why if we take some number x to some prime minus 2, this will give us x inverse, the multiplicative inverse of x under some mod. So that lets us do division, and then we can comfortably do fractions by storing P times Q inverse without worrying about the fact that adding and multiplying might be tricky. And then addition, subtraction, and multiplication are all very self-explanatory and easy to understand why they work under mod. So hopefully this lets you, if you're afraid of doing problems that have big mods in them, hopefully this kind of resolves those fears, because I know I was certainly afraid of them when I first started doing competitive programming in high school, and actually understanding what was going on helped with that very much. So last thing I'd like to mention is, now that you know how to do division, you can do n choose k. And n choose k is just equal to n factorial over k factorial times n minus k factorial. This shows up a lot. This is the number of ways to pick k things in a set of n things. And in order to do this, if you have like some big mod, you need to know division. So you can calculate all of your factorials in like some array. You can pre-compute that. And then you can calculate the modulo inverse of each of these factorials by taking it to the power of the mod minus 2. And now this resolves into just two different multiplications. You multiply n by k factorial inverse, or n factorial by k factorial inverse, then multiply that by n minus k factorial inverse. And that will give you exactly what you're looking for. So hopefully that made sense, and you're good to go. Thank you for watching, and good luck on the next round.